All right, so last time we ripped through TCP and IP to show like how the internet works, how our packets are getting from point A to point B. Man, that flashing drives me nuts. I was hoping it was just a one-time thing when I did that on Monday. Thought I'd try. So we learned about those, and now we're starting to learn about HTTP, which is the protocol, the main protocol that we're going to be worried about in this class. This is the one that you'll have to code up on your homework. By the way, homework one is released if you want to start looking at that and start getting started. But HTTP is what we're going to start coding in. So you're going to start your TCP socket server and start writing some HTTP parsing and writing code. So when you get an HTTP request, you're going to connect to your TCP, connect to your client via TCP, and you're going to just get bytes over that TCP connection. The internet can only speak ones and zeros. So all you can do is read bytes off of that stream, and we have to make sense out of those bytes. So HTTP is going to be our way of making sense of those bytes, and mostly we're going to interpret those bytes as strings. So we're going to decode the bytes as strings. Not always. Later in the semester it'll be different. But we're going to decode them as strings and then do a lot of string parsing to figure out what these HTTP requests are actually requesting. So there's two different forms of an HTTP request, which I might actually skip through some of these lines. So this was the overview slides that we didn't finish last time, and today's slides go in depth on these things. So I'll skip some of these overviews since we're about to go in depth. Content length and content type, yes. Yep. Good. Fine. I think this is the one point I want to harp on a little bit. HTTP is a stateless protocol. I was mentioning this on Wednesday. I want to keep reminding you until I bash it into your heads. HTTP is a stateless protocol. That means you're handling every single request in complete isolation. So even when the same user is making 5 requests to load one web page, when you have 5 requests, one for the HTML, for your CSS, for your JavaScript, for a couple of images, you're treating every single one of those requests in complete isolation. Your server doesn't know or care that all those requests were coming from the same user, and that user is actually just requesting your entire web page and assembling that web page on the other end. You don't care. You're just going to say, oh, I got a request for my JavaScript. Here's my JavaScript. Oh, I got a request for the CSS. Here's my CSS. You don't have any code that says, oh, looks like somebody's loading my entire web page. We don't care. We just don't care. I mean, you can write code to figure that stuff out, but HTTP, the protocol itself, doesn't care. All right, so let's get into today's slides. I got to refresh, but if you refresh the page, homework 1 is posted right here. This is where each homework will be posted for each section of the course. They'll be posted right here. Homework 2 will be right here, for example. So homework 1, if you want to take a look at it. I don't think I'll have time to really talk about it right now, because I want to get on track. We fell behind from day 1, and I don't like that. I don't like falling behind. I want to be right on track. So HTTP requests and responses. This is what we want to start talking about today in more depth. We did just talk about it in overview slides, but let's start talking about it in depth. So I think one of the most important things about this course, or web development in general, are the RFCs. So RFCs, or request for comments, these are where most of our internet protocols, including IP, I guess, but most of the protocols that we use as web developers are going to be defined. So for example, RFC 2616, which I have linked on the course website, this RFC defines HTTP. Everything you want to know about HTTP is defined in that document. That document defines HTTP to the point where if I say something in lecture that contradicts the documentation's right. That RFC is your ground source of truth about the protocol. There's an RFC for IP, for TCP, for HTTP, for HTTPS, for WebSockets. Everything we talk about in this class, there's going to be an RFC that will be your source of ground truth. So if you ever have a question of how to parse these headers, how to parse the body, how to parse and write HTTP requests and responses, the RFC is your ground source of truth. And it's important to have this because the browsers, any browser developer has to implement HTTP according to the protocol, and any web server has to implement HTTP according to the protocol. If everybody on both ends is looking at the same RFC, we can have effective communication using HTTP. So that's your ground source of truth, RFC 2616, very important. We'll specifically talk about sections 4, 5, and 6 in today's lecture. The 4, I believe 4, I shouldn't even say this because I'm not sure. 4 is the format of an HTTP message. 5 is specifically requests, and 6 is specifically responses. I'm like 99% sure that's what each section is. But those 3 sections combined are HTTP requests and responses, which is what we're talking about today. Yep.
So RFCs are good for like organizing between devs, developers?
Yes. And it is where the standard is defined. Like that RFC, when that RFC was published, that was somebody saying, I came up with this thing called HTTP. Here it is. Let's talk about it. And then refine the standard over time and then finally publish it and say, this is the standard. So it's not like a resource that's like explaining the standards or anything like that. It is actually where the standard was first defined and where it remains defined. It is our actual source of truth of how these internet protocols work. Yeah?
Can anyone write them? Like, can anyone just put one out and then people just kind of like ignore it?
I never really thought about that. Maybe. The question is, can anybody write them? I wouldn't see why not. Maybe there's some sort of vetting process, but I don't know how strict that would be. I mean, if you have a good idea, I'm sure they'll listen to it and take it. So when I introduce new topics, I'll typically link the RFC in the course website. Well, they're already linked, but and that's, like I said, your ground truth. If you're coding something, you're coming across some really strange bug, or you have a specific coding question when you get to a certain part, a situation that you're just not sure of, the RFC will have your answer, either that RFC or another RFC. For example, there's certain specific types of requests, like multi-part requests that we'll see in homework 2, that has its own separate RFC, not in HTTP. But the RFC is always going to have your answer. If it doesn't, let me know. We can draft a letter and tell them, hey, you need to update your RFC. New lines in HTTP. This is something I'll say early and often. New lines in HTTP, requests and responses, anything related to HTTP, are going to be a /r/n character. So new lines, when they're displayed visually for us, it's just going to look like a regular new line. You know, there's text, and then on the next line, there's more text. It just looks like a regular new line to us. But the bytes of that new line are actually 2 characters, which is a /r and a /n. The /n is our regular new line character that we're used to, but we have this extra /r, which is a carriage return, which is frustrating that this is the case, but hey, this is a standard that's out there and it's been out there forever. It's not something that can be easily changed. So we're stuck with this for the foreseeable future. Carriage returns from the days of typewriters. When you got to the end of a line on a typewriter, you would have to return, the carriage is the thing that's actually doing the typing, and then you would return the carriage to the first character of the line, and then do a line feed, which would be advancing to the next line. So that's where it comes from, and in certain architectures, certain systems, certain parts of computer science, we're kind of stuck with this, and HTTP is one of them. We have this carriage return line feed, often referred to as a CRLF in the RFC. CRLF, which sometimes I'll refer to it as, because it rolls off the tongue pretty nice, more than /r/n. I get sick of saying that, so sometimes I'll say CRLF. I mean the same thing. I mean a new line character in HTTP. So be aware of this. When you're parsing requests, You have to be aware that that /r is in there. You can't just split on new lines because you have these trailing /r's on all of your strings. And when you're writing responses, you have to make sure you have your /r/n, your CRLF, in all the new lines that you send in your response, or else the browser's not going to be able to read your response. Very important whenever we talk about new lines. Visually on the slide, I'll just show the new lines, as we like to consume content as humans, just as a physical new line. But there is a CRLF at the end of each line. So let's talk about HTTP requests. When somebody requests information from your website, so this is going to be the format of a request, a very, admittedly, very simple, straightforward request for this one. Obviously, it's our first request example. We'll get this request from the browser. Yeah.
So CRLF basically replace all the new line characters, or does it happen only in specific cases?
It's in any HTTP request or response, the new line characters will be that /r/n. It'll be 2 bytes.
So the content does not change, right? With the CRLF? The actual body of the
The-
message does not change.
So this is in, oh yeah, good question. So this is in the headers of the HTTP request. Once you get to the body of the request, then that doesn't apply anymore. So like if I'm sending HTML, that HTML doesn't have to have the /r's in there, but the headers, the parts that HTTP is concerned about, all has to have the /n, or /r, I mean. /r/n has the same number of syllables as CRLF. Yeah, but CRLF just flows a lot better. /r/n, it's rough to say. Yeah, that's going to be why you see that in Wireshark. Mr. Dr. Professor Carriage. So in actuality, what the request is going to be, these are going to be the exact bytes that you're going to read. When you write your code, you're going to have a TCP socket connection, and you're going to say, give me some data. It's going to give you these bytes, this sequence of characters as bytes. You're going to decode it as a string. And this is exactly what you're going to see if this were the request that was made to your server. You're going to have those /r/n's, and importantly, there is a new line, a blank line at the end of a GET request, which signifies this request is over. The next bytes that you read are going to be another request. Unless it's a post request and there's a body, that's where that'll go. We'll talk about that in a second. So this is what you're going to read. So keep that in mind when you're parsing these requests. If you're, say, splitting on /r/n, you're going to have the last value in that array after splitting is going to be an empty string, for example. Something we need to be aware of. You'll have an empty string. If you're splitting this, you'll get this line, and then an empty string. So if you see those empty strings, you know what's up. Yes, this is, so when the browser makes a request to your web server, this is exactly what you're going to see, something in this format. It's exactly what your web server is going to see, and then we want to parse this to figure out what to send back as the response to that client. Yeah?
Sorry, that's the request that our browser sends to your website when we put in the URL or how to go for it?
Yes. Yep. And actually, let's demo that a little. So I'll go to my same example from last time. Let's, so when I go to google.com, where's my button? Do I not have that in Opera? Or is that only on post requests? I want to view the raw headers. well, we might have to wait till next week for a better demo.
Maybe it's initiated.
Let's table that until I have a demo all set up. I'll have it for next week when we start dumping into code. I'll have a good demo set up. I was trying to do a quick one there. Usually there's view raw, which shows you exactly what was sent over the wire. That view is giving us all this information, but already parsed. All right. So let's talk about the parts of an HTTP request. So we know that we're going to get something that looks like this, but let's talk about what exactly we're looking at. So the very first line, everything before the first CRLF, is going to be the request line. This is going to have 3 pieces of information that are all separated by spaces, which implies that you can't have spaces in the values of these 3 things. So we're going to get 3 pieces of information. First is going to be the request type. Is this a get request, a post request, a put request, a delete request, a head request? What is being requested? What's going on here? The next, then followed by a space, and then the path of the request. So remembering our URL format, we have the protocol, the host, the port, and then after the port, we have a slash, and everything after that slash, including the slash, is going to be the path. This can include our query strings in fragments as well, which I didn't talk about really in any depth. But everything after the port number is going to be the path. That's going to go right there in between our other 2 values in this request. So right here, we have just a slash for the path. So it's going to be a request for typically our home page, which is typically an index.html just by convention. But it doesn't have to be. It can be whatever you choose it to be. Oh, that's my next slide. And then the HTTP version is going to be the 3rd value. For this course, we're just always going to use HTTP 1.1. We're not getting into different HTTP protocols. So it's always going to be HTTP 1.1. If you just want to assume that it's 1.1, I'm fine with that. You don't have to parse this and say if HTTP/1.1, then do all the stuff, else don't do anything, or say version not supported or whatever. We don't have to do any of that. You can just assume this is 1.1. And when you send your responses, you always send your responses as HTTP 1.1 responses. But what's important for you to parse is these first 2 values. So you get a request, you got a brand new HTTP request that you read off a TCP socket. You're going to look for the first line. You're going to look for that first CRLF, and everything before that is the request line. Split that on spaces. You're going to expect 3 values. The 3rd value you can just assume is HTTP 1.1. But the first 2, you want to get the request type and the request path. And based on those 2 pieces of information, that's what's going to determine what you end up sending. So for example, if it's a get request for slash, your root path, probably going to send your base HTML for your home page. If it's get style.css, you're going to read your CSS file and send the contents of that to the user or whatever else they're requesting. So I already got ahead of my slide here, but if it's just a request for slash, that's typically where you're sending your home page. By convention, index.html is usually what our home page is, but it's literally whatever you code. It doesn't even have to be a file. You can hard code your HTML. It's whatever you decide to send. But by convention, slash the root path, that's going to be your home page. If that path is something else, somebody types in CSE 312.com/lecture, then we're going to get that path in the request line. The request line is going to tell us what specific resource was being requested. So very important to parse those 2 values. And typically, when you start writing your homework code, you'll have a big else if block where you'll say if request type equals get and path equals slash, return my home page, else if request type equals get and path equals style.css, return my CSS, etc. There are ways to avoid the big else if block, but if you just want to do a big else if block, I ain't going to judge you for it. When we get really late in the semester, the else if block gets hard to maintain, but You'll see when we get there, when you get to that point, when you have a lot of code in a else if block. And then finally, after that first line, there's any number of headers. HTTP headers. This, I recommend you write header parsing code following this format as soon as you can. Right when you're parsing your first header, write generic code that's going to parse all headers, because we're parsing headers all semester, baby. So a header is going to be on its own line. There can be any number of headers. This request only has one header, but there can be any number of headers separated by new lines. Headers are going to be key value pairs, and the key and value are separated by a colon and an optional space. If you read the RFC, it says there may or may not be a space after the colon. If there is a space, you should be getting rid of that space. It's not part of the value of that header. Headers can't start with a space as their value. According to the protocol, those spaces are optional, so this space might not be there. It might be there depending on your browser, depending on how, whoever sent you the request, how they coded their HTTP request code. It might be there, might not. If it's there, remove it. If it's not there, there's nothing to do. I've always seen that space there. I haven't experienced a browser that doesn't put that space there. So just be aware that space is going to be there, but it's not part of the value of the header. So this is a header named host with the value CSE312.com. So writing code that reads each line of this request, looks for that colon, separates the key and value, and puts them in some key value store will benefit you throughout the semester. Then you don't have to be parsing headers all semester. You write that code once and be done with it. And then there's a new line, there's a blank line at the end of this request, which says that's the end of the request. Once you see that blank line, that's how you know you're done parsing headers. Yeah?
For assignments, are we able to assume then that this protocol is followed?
Yes, absolutely. So you'll test your server by opening up your browser and going to your website. And the browser is going to make requests. If you're using any browser, it's going to be following HTTP. Yeah, in this example, I do have a space there. It might have a space. I've always seen the space there, but that space is optional. If that space isn't there, this header has the same exact key and value. It represents the same exact information. In RC 2616, right? I can't believe that. All right, blanking on that. In that RFC, it says that explicitly. It talks about the spaces. And it's like the headers can have spaces after the colon. They might not. They might. It should be removed if it's present. It's part of the standard. All right, so we get this request. We got a specific request type and a path that's being requested, and we need to send a response back to this user, back to this client. This response is going to be a very similar format. Specifically, the headers are in the exact same format. There's going to be headers that we need to send. But there's a little bit more to talk about when we're sending these responses. So first, remember we have these new line characters, the CRLFs. This is what exactly is going to be the response that we're sending here. No CRLF at the very end of this one. I'll explain that each line as we go through. So first, the very first line of your response is going to be a status line. It's similar to the request line, but it's going to be just a little bit different information in different order. The first value is always HTTP, for our purposes, HTTP 1.1, the HTTP version number. Every response you send back is going to start with the characters HTTP/1.1 space. So just like the request line, we have three values separated by spaces, HTTP version. Then the status code. I kind of skipped this slide in the other deck, but this is a code that tells the browser or client, if it's not a browser, kind of what happened with this request. In most cases, you're sending back 200 code responses, which means, bless you, which means everything went fine, everything's good, here's the stuff you asked for. That's a 200 response. It's a response code that, just using the internet, you'll never see, because if you get a 200 response, you're just seeing the content that you requested. Everything went great, and you're just navigating the internet as normal. And then finally, a status message. This is a human-readable explanation of what the status code means. So 200, the browser's reading that. That code has to be exact. It has to be whatever the browser, whatever the browser's going to do with that. But then the human-readable status message is going to be whatever you want to say to the user. Now, this should match what the standard is. Like 200 is capital O, capital K. That's the status message for that code. You really should follow those, but things don't break if you don't follow that. Yeah.
Is the handshake already done?
Yes, the TCP handshake. Yeah, that's already done before any of this even begins. The status message can have spaces. So when the browser is parsing this, it's going to look for the first 2 spaces, and anything after the second space is the status message. So when we send back a 404 not found can be 2 separate words. That space is allowed for what it's worth. And then we have our headers. When we're sending a response with content, we need at least these 2 headers. These 2 headers are going to be required. You're going to be writing these headers all the time. The content type and content length, capital C, capital T, capital L, dashes in between separating the words. Content type, content length. This is going to tell the browser about the content that you're responding with. So for example, somebody makes a request for your root path, just slash, and you're going to respond with some HTML. This is where you would say, look, I'm sending you HTML, so you know how to parse this, and I'm sending this many bytes of data. So content type. Hey, browser, this is the type, bless you. This is the type of stuff that I'm sending. In this example, it's plain text. So we're going to do text/plain to say, this is plain text that I'm sending you. We'll talk about a bunch of different content types. For today, suffice to just use text/plain will be what we're doing, all we do for this. For task 1 on the homework, you're just sending plain text. So you can get started on task 1 today. And content length, the number of bytes that are in the body of the response. This can be different than the number of characters. We're sending a string hello. It happens to be 5 characters, happens to be exactly 5 bytes. But this is the number of bytes in the response. Remember, we can't send anything except 1s and 0s over the internet. So when we're sending information over the internet, it's all 1s and 0s. For our purposes at this point in time, it's all bytes. We're going to send 1s and 0s in chunks of 8. Always bytes. So when we send this over the internet, it's going to be a bunch of bytes that happen to represent a string. So we're going to say, hey, these bytes actually represent a string, and this is how many bytes are representing that string. Yeah.
One character tends to be a byte long, right?
If it's ASCII, if it has an ASCII equivalent, it'll be 1 byte. I have a whole lecture. We'll talk about that. I think it's next week. I don't think it spills over to the following week, where we have Unicode characters that don't have ASCII equivalents. Those will always be more than 1 byte. So, for example, if you're sending like text in non-English that doesn't use our English alphabet of 26 letters, if you're sending any text that doesn't use that alphabet, it's going to be more than 1 byte per character. Yes.
When you are sending a file for the content, do you mention the size of the file or the amount of ASCII?
If you're sending a file in the response?
For example,
Yeah. So then the content length would be the number of bytes in that file. Yeah, the TCP socket, yes, is just the device that lets us send. Once we have a TCP connection with the client, that allows the client to send bytes to us and us to send bytes to the client. That's all TCP is doing for us. So TCP is all set up, and then we get some bytes over the TCP connection, and we treat those bytes as an HTTP request. So we're going to parse those bytes using our HTTP protocol, then we're going to send bytes as a response over this TCP connection. That's going to be our HTTP response. So content type, content length must be there. This tells the browser how to parse our information. And then finally, the body of the response. This is the actual content. This is the first time we're actually getting something done. We're sending something to the client and saying, here's your information. Here we're just saying hi. This is a hello world example. We're just saying hello. The content is going to be after the headers and separated by a blank line. So when the browser gets our response, it's going to look for a blank line, which is 2 CRLFs. That's going to be our blank line. And everything after that blank line is going to be the actual content that we're sending. And the content that we're sending is going to be of this type and has to be this many bytes. To the extent where if we have our content length off, if our content length for this is, say, 2, and we send that as the response to the browser's only going to read 2 characters of our response. It's not going to let me just highlight 2 characters, but is only going to read 2 characters, and those extra 3 bytes, those extra 3 characters, they don't get read. The browser's going to read exactly content length number of bytes. Yeah.
What if the content length is larger than the amount of bytes? Will it just start reading randomly from memory or something?
It would read off of the TCP stream. So if we have another response that we're sending to that same client, it'll start reading the status line of the next request and the headers of the next response. The headers of the next response, up until however many bytes. If we aren't sending another response, if we haven't sent anything more, the browser just hangs. So it's important that however much content you're sending back, it's important to make sure your content length matches. If it's too low, the client's going to be missing some content. If it's too high, browser hangs. So we got to make sure that that's exactly the number of bytes that we're sending. Yes?
So if we're starting a connection to a website, would the body just be the HTML first response?
Yes. Mm-hmm. And the content type would be text/HTML, and the content length would be however many bytes your HTML has. Yeah, it's our first request and response, so I'm doing just hello world. Trust me, we will get into HTML, CSS, we'll get into all of that. We'll do all of it. I can't do all that in one lecture, though. Today we need to understand how the format of these requests and responses are going down. And for what it's worth, task 1 on the homework is responding with hello. The first part of task 1, I should say. Response codes. We have a lot of different response codes. I kind of glossed over the slide earlier, but you probably heard of a lot of them. 404, content not found. 301 is a redirect, which we'll talk about both of those ones today. But we have these categorized into different categories. Any 200-level response code, so a response code that starts with a 2, this means everything's good, everything's cool, nothing going wrong here, we like what's happening. If you're responding with a 300-level response code, any response code that starts with a 3, this is a redirect response, or for any reason that we're not sending content. For example, if the content that was requested is already in your browser's cache, if that's already up to date, you'll respond with a 300 level and say, you're basically a redirect to your cache. You already have this information. We'll see a 301, which means this site has moved permanently. We're going to redirect you to another site. Anytime where we're not responding with the requested data, but we're telling you where you can find the requested data. 400 level errors are errors by the client. 404 means the client requested a resource that doesn't exist. 403, the client requested a resource that they don't have access to. These are anything that the client did wrong, and we're letting the client know, here's your 400 level error. You did something wrong. Fix what you're doing at that point, which often, like a 404, is often a server-side error anyway. If you click a dead link, like somebody made a mistake somewhere that wasn't the client, but that's generally what the 400 levels are. And then the stuff of nightmares, 500 level errors. This means there was an error on the server side. This is the stuff that, as a web developer, can keep you up at night. You get that call at 3 in the morning. Hey, clients are getting 500 errors. Something's breaking. The database is down, or whatever it is, and you got to fix your shit like right then. This is the nightmare stuff. Whenever we start getting 500 level errors on Autolab, for example, bless you, I got to drop whatever I'm doing and fix that shit, because that's no good. We can't have 500 level errors. It means something very serious is wrong that the developers have to fix. The 500 level errors give me nightmares. It's one of the codes that we'll use, starting with homework 1, is a 404. You requested a path that doesn't exist. So to test this, we'll go into the browser, go to your, make a request for your website, and just like smash the keyboard and hit some random path, and make a request for a random path. Your server should see that and say, hey, I don't have any path matching this. Typically, you're going to say, like, if this is a GET request for / send my HTML, else if this is a GET request for CSS, send my CSS, JavaScript, etc., all the paths that you're asked to code in the homework. And then at the very end, you'll have that else. You'll say else, send them with the 404. Your request didn't match any of the stuff I have coded here. It must not exist. Here's your 404. Try again. 404, you are going to send a message. You're going to include a body. You'll actually have content for the 404. It'll be whatever 404 message you have. Most sites have a full HTML page for their 404s with cute doodles or whatever. You've seen them before. Here, I'm just sending plain text and saying the requested content does not exist. So when the user gets my 404, they'll actually see that text in their browser. The requested content does not exist. And finally, a 301, the other one, another one that we'll use in homework 1, is a redirect. So this is when the client requested a path, and for whatever reason we move that path. It exists in somewhere else or a different website or whatever. We move that stuff. Which I wish this were used more out there on the internet. I hate having a dead link because they move stuff. Like if you're going to move something, have the old link respond with the 301 to say where that new stuff is. I hate having dead links all over the place, especially like updating my course websites, and half the links are dead because they moved content around and switched their pathing structure without putting 301s on there. But 301, we're going to respond with the 301. Once the browser sees this 301, like the moved permanently, that's for humans to read, that's for us to read. But the 301 is for the browser. Once the browser sees a 301, it's going to look for a location header. The location header is required when you're responding with a 301, and the browser's going to make another request for that new location. I should put a bounty out on this thing. This is frustrating, but put a content length of 0. According to the standard, according to HTTP, if you don't have a content length, the content length should be assumed to be 0, and it should be assumed that there's no body to the request. In most cases, this works. If you just don't have a content length here, you'll get a request for the new path. Everything's fine, except in Firefox. And I don't know why. If anybody can figure this out, I would love to know. It's been an issue for, I've known about this for over a year, semesters of doing this course. It's always a problem. If you put content length of 0, Firefox is fine. It'll redirect normally. If you don't have a content length of 0, Firefox will hang on a 301 response. I don't know why. I'm quite certain Firefox is in the wrong on this one. but I can't figure out what exactly is going on, or I couldn't find anybody else talking about it online. I searched for a while. Some reason Firefox only.
Do 301,
Yeah, go ahead.
the 301 request like actually automatically make a new request for the given path, or do you have to like set that up?
No, it'll automatically do it. So the browser is going to make a request. You respond with the 301. The browser is going to read that location and make a second request for the new path. So this new path can be either a relative path or an absolute path. This is an example of a relative path. I'm just saying /new path. I'm just giving another path to be requested. If you just give a path, the request is going to be made using the same protocol, same host, and same port number, and just the path of the URL is going to be changed. So if the initial request was for CSE312.com on port 8080 with some old path, and I respond with my 301, it's going to read, the browser is going to read the location and make a new request with all the same URL up until the path, and it'll replace the path with the new path and make a second request. If you don't want that feature, you can use an absolute path and include the full URL, including the new host, the new protocol, the new port. If the ports, I should mention since I'm showing port numbers here, if the port's not specified, the default port for the protocol will be used. HTTPS, this is an HTTPS request, so this request will be on port 443. Oh my goodness, I'm blanking on that. And if it's an HTTP request, the port will be default to 80. So if you don't want to use the default port, you specify the port explicitly with the colon. But if that's absent, the default port is used. So specify the entire URL. Now the second request is going to be for google.com. And I'm saying, we redirected, we completely changed our domain name, go somewhere else. I even changed the protocol from HTTP to HTTPS in this example. I'm saying, get out of here. We moved completely. Yeah.
If you use the relative path, does it get added to the default port that it originally called from? Or
The same port as the original request. So you have a request and you responded with a 301. That initial request, same port as that request.
Okay. So if you're like on dash new and then you try to call dash new wherever, it will send you to the
Yeah.
it will still have the original dash new if you're calling from dash new.
But
If you're
so
calling from new path and you ask for like new path, but you get sent to a different one, will that add it on to
it'll replace the path entirely.
Okay.
So to replace the path, everything after the port number is replaced with whatever your relative location is. And finally, post requests. This is where the user is sending information to us. The structure of this, very similar to a GET request, except we do have content, and that content is going to follow partly what our responses look like. Namely, it'll have a content type, a content length, and a blank line separating the headers from the content itself. So very similar to the responses that we're sending, except the request line is going to follow the request line protocol that we saw in GET requests. So when you have a post request that you're receiving, you're going to expect, first of all, the word post here, but you're also going to have a content type and content length telling you about the actual content of this post, of this request, a blank line that you have to look for, and then everything after the blank line is going to be the content that you need to read. And of course, it's going to have the CRLFs. I already said that. Damn it, slide, I already said that. This will be much more important later in the semester. I have the assignments designed so you don't run into this on homework 1. But starting homework 2, it'll be important. You have to read that content length, and after you read that CRLF, make sure that you're reading content length number of bytes. If you haven't read that many bytes, you're not done reading the request yet. And you have to go into a buffering state, go back to the TCP socket, and read more information because there's more information sitting there waiting for you to read it. Homework 1, you won't have to worry about that, but I have multiple lectures. We'll talk about that at length later in the semester. All right, that's my last slide. So any questions? The search bar on YouTube is actually a GET request using query strings. But when you fill out a form, like when you log in, for example, that would be a post request because you're sending your username and password in the body of the post request. All right, so we got one more thing to do. And it's an exciting one. So I still have it saying not yet active. I thought I deleted that. So Autolab is active, and you should all be added into Autolab. And we have our first lecture question today. So if you go into Autolab, September 2nd, you'll see this form. It just says A, B, C, or D, or E. You'll select whatever your response is, affirm that you didn't cheat, and then submit. And the question is this one. There's one pretty tricky answer in here. I tried to repeat it as many times as I could in lectures. Hopefully it doesn't trip you all up. And I'll typically do the lecture question as the last thing in lecture. And once you submit the question, you're free to go. So that's all I got for you. Have a great weekend.